So last time we got to the Adeles. Adeles are the set of all things that look like x infinity, x2, x3, x not 4. So that each for all p less than including infinity xp. What's that?
Stop the dots early.
Yeah, right. One more. So that the x's are all in each QP, with the caveat, of course, is the restricted product. So this is the restricted product of R and all the QPs, restricted by the fact that for almost all P, XP is actually not in QP, but in ZP. So almost all in this context means all but finally many. Almost all. Yes, it's just we're gonna see this again and again, so I'll introduce some notation for it. All but finitely many. Okay, there's a natural topology on the Adeles. These are the Adeles. The Adeles form a ring. This is the ring of Adeles. This is the restricted product. Okay, we don't need to say that. Topology is generated.
Not a division ring.
It's not a division ring. Topology generated by things of the form product of some UPs at a finite number of places. These are just opens. We know what it means that we already have topology on each of the QPs, including R. So you can take a finite set of opens cross everywhere else we take ZP. Okay, for S, it's a finite set, and UP open in ZP, in QP, including infinity if necessary. Okay, so these are the open sets. In that topology, in this topology, Q itself, which embeds embedded diagonally.
Which means just putting it in every slot.
Yep. There's an embedding of Q in every QP, and it will be in ZP for once you're past whatever the denominator was of that particular rational number. In this topology, Q, which is embedded diagonally, is discrete. And the way we saw that was that the set -1 to 1 cross all the ZPs contains only 0 and no other rational point. Contains only 0 because all others have Adelic norm, by which I mean the obvious thing, you multiply over all primes, including the infinity of the p-adic norm. By our nice normalization, this is 1 except for 0. And this set has norm strictly less than 1. So no other rational points can be. Okay, and then we were trying to figure out, I think this is as far as we got, right? We were trying to figure out a fundamental domain. So we have a discrete subgroup acting on the additive group of the Adeles. And we wanted a fundamental domain for the additive action of Q on the Adeles. Right? That's as far as we got. By the way, I asked, I don't know how to use like stack exchange and whatever math overflow, whatever you young people use. I have my own stack exchange called Keith Conrad. So I wrote to him and said, what's the history of all this stuff? And so, right, it seems, actually, there's something very interesting. So Artin, Emil Artin, when he fled the Nazis, of Michael Artin, or
yeah,
he's the father. So he in 46, he was teaching in Indiana, just FYI, and he had a student named Margaret Matchett. Margaret Matchett. And she wrote a thesis. Is that 2 T's? I think it is. And she wrote a thesis on ideles, understanding Hecke zeta functions, whatever those are. I realize these words don't have meaning for us yet. In terms of ideles. And then Tate took over from there. So Tate's 1950 thesis was, if you do this with Adeles and you take, well, you need Adeles and ideles because you need a Mellin transform of a Poisson summation formula. So if you do an Adelic Poisson summation formula, this is what we're building up to. Adelic Poisson summation, maybe even today, we'll see. Plus Mellin type transform, for which you need ideas on ideles, Mellin type, Adelic Mellin transform will recover the Hecke zeta functions and everything else. Basically gives you automorphic representations on GL1. That's not how people thought of things back then, but it becomes the theory of GL1 Adelic automorphic representations.
Why? The other question becomes, why did Arden and Matchett start thinking about this?
Yeah, it's a very good question. Well, you see Arden sort of feels like there's something there, and he keeps giving different students this problem to get it, to see how far they can get. Curiously, so I recognize this name immediately. My friend Melanie Matchett Wood is married to Philip Matchett Wood, who Philip Matchett was a PhD student at Rutgers, and his 2009 PhD thesis is dedicated to his grandmother, Margaret Matchett. So there you go. So there's a Rutgers connection to all this stuff. Right, and it's really not until now, I called this thing an automorphic representation. It's not. So in it's funny how this stuff is all happening around the same time. 1947 is Bargmann's classification. So Bargmann, well, I don't know why I'm telling you all this. It'll become relevant when we get to it. Classifies all irreducible representations of SL2R, PSL2R. This becomes an important component. Naimark actually, around the same time, Gelfand and Naimark. Yeah, and Gelfand and Naimark. Gelfand. Naimark. This is happening at the same time. So before we can get to Langland's, we need to get to the notion of an automorphic representation, and especially an Adelic one. So the Adelic side of things and the number theoretic side of things is happening in Tate's thesis. The representation theory side of things is happening at the same time in this work, beginning with Gelfand, Naimark, and then of course Gelfand, Greif, Vitesse, Shapiro. The thing that we're trying to build up to is apparently by the 62 ICM of Gelfand, ICM lecture of Gelfand, you already have the GL2 automorphic representation theory, GL2 on the Adeles, and this becomes the book of Gelfand, Greif, Vitesse, Shapiro, Gelfand, Greif, Vitesse, Shapiro, which is taken up by Jacquet and becomes the Godemann-Jacquet L function and Jacquet-Langlands and then Langlands sort of which turns into Langlands. Okay, so anyway, that's a little bit of the history of this stuff. FYI. So these ideas of it was kind of in the ether. It was kind of in the ether all around the same time. All right. But it does seem to be that Tate was the first one to actually execute Poisson summation, for which he needs Fourier analysis. So this Fourier analysis on these groups really does seem to be original to Tate. Although so much of it was worked out, so much Fourier analysis was worked out in other contexts before, Pontryagin, the notion of Pontryagin dual and so on, that it was kind of all ready to go when Tate needed it for this application. Anyway, all right, we wanted to find a fundamental domain for the action of Q on A. In other words, i.e., I gave you, what is a fundamental domain? Right? What's a fundamental domain? If I have the reals and I have the integers active, it means I give you any real number, give me the simplest representative of that number. give me the simplest, whatever that means, right? If there's a set of simplest numbers, simplest representative, let's say in R of a Z coset, right? That's if we're talking about R mod Z. So a simplest representative might be, well, you take your favorite number, X is 3.14, 159, whatever, yada, yada, right? And the representative that you'll give me is 0.1415 now, right? So a fundamental domain will be shift by the integer value of the floor function, right? Shift by floor function. Shift by floor function into the set 0, 1. And that's a nice fundamental domain for the action of R mod Z. So that's what we're looking for. We're looking for a nice, a simplest representative. So what's a simplest representative of an Adelic number?
Do you want to like copy and paste the formal definition?
Of a, yeah, do you want to remind you what a fundamental domain is?
I mean, you wrote it last time. So
Yeah, it's easy enough to write it again. Recall, D is a fundamental domain. Again, there's some choice about how to define this. Do we want it to be open and any point can be moved into its closure? What I've written is neither closed nor open. D is a fundamental domain for gamma acting on a space X if two things are satisfied. For all X in X, there exists a gamma in gamma such that gamma X is in maybe not D, but its closure. If D is, let's say, open. And 2, for all X, Y in D, not just in X, but in D, and gamma in gamma, gamma X equals Y implies gamma equals the identity and X equals Y. These are the two conditions that say you can bring any arbitrary element into simplest form, and there's a unique way to do that. If two elements are in the fundamental domain and differ by an element of gamma, they're the same element and gamma is the identity.
Is it possible that gamma is not identical, but it just takes that as gamma axis?
If there's a stabilizer, you will want to mod out by the stabilizer. That's part of the reason why we prefer PSL2Z acting on the upper half plane than SL2Z. So you want to mod out by a stabilizer if there is one, so that so this action is simply transitive.
And then, so in this case, gamma is just the addition.
In our case, gamma is addition. Yes, I've written the group law as multiplication, but in our case, yeah, for us, we want such a D for Q acting Q. Okay, so Q, an element Q in Q maps X in the Adeles to Q plus X in the Adeles. That's the sense in which it's an action on the Adeles. It's just translation. Okay, diagonal translation. How can we make an X in the Adeles as simple as possible? That is a very good guess, and that is exactly why I wrote this set again here for us to be able to stare at. So certainly a product of the ZPs cross minus 1, 1 is a good candidate for our simplest possible set because it only contains 0. That's almost right. That's almost right. So let's build up to that. In order to so here's a guess. I like your guess. So Jishen's guess is maybe the domain is, let's say, minus 1 to 1 cross product over the primes PZ. Okay, so if I give you an arbitrary, so given arbitrary X, which is X infinity, X2, X3, X5, I wrote it this time. Find Q in Q. Can we find a Q in Q such that I can get inside this domain? So this is our guess for a domain such that X plus Q, if you like, is in the domain, right? Can we translate by some rational number? Now, in order to be in the domain, I need every single XP, i.e., the norm of XP plus this fixed number Q in the pth valuation, in the pth place, is at most 1. That's what it means to be in ZP. Right? ZP is the set of all things whose valuation is less than 1. So if I have anything in front, in other words, if XP looks like a minus n p to the minus n plus a minus 1 p to the minus 1 plus something in ZP, I need to kill this off. Exactly. Need to kill this off. Then need to kill off, add or subtract, kill off this part by adding Q.
Oh, so this is why you were saying Chinese remainder.
Aha, that's exactly why we need the Chinese remainder theorem. Because we need to do it at all of the primes simultaneously, but not all, only finitely many.
Right.
Okay, need to do this simultaneously with a single Q, Q over only finitely many primes, right? P, let's say in a set S. S is the set of primes such that XP is not in ZP. And that's exactly what the Chinese remainder theorem, let me remind you what we said. We proved it last time, right? We did this. Yeah, we proved it. Given P1 to the E1, Pk to the Ek, powers of distinct primes, and any choice of Cj in Z mod Pj, Ej, any choice of residues, I don't care what residue you take, there exists a solution X in Z, there exists such that, which solves the equation X is congruent to Cj mod Pj to the Ej. Okay, we can solve all of these residues, the simultaneous system of equations. Does that make sense? So you can see why we would need such a thing. So how are we going to do this? How are we going to kill off all of these things? Well, first of all, let me tell you something called weak approximation. So this is called weak approximation. In fact, this is weaker than weak approximation. Let me call it weaker approximation. Weaker approximation. This is not standard notation. Weaker approximation is that given C1 through CK, what's a good way of indexing these? Given, let's index them by a set. Given a set S and a CP in QP for all P and S. Okay, you give me arbitrary points. In fact, let me make them in ZP. You give me a finite set. Of course, S is finite. You give me a finite set of places, and for every place, you give me an element of ZP. There exists a Q in Q. There exists a rational Q, a single one, such that, given an epsilon, this is the approximation, given any epsilon, I can approximate simultaneously all of these CPs with a Q to error epsilon. There exists a Q in Q such that CP minus Q, the p-adic norm of the distance from one to the other, is less than epsilon. It's like an API. That's exactly what this is. It's like an API theorem building up to the fundamental domain. Exactly right. This will build up to the next thing, which will build up to the next thing, which will build up to what's called strong approximation, which tells exactly what the fundamental domain for the action is. Okay. So how would you prove such a thing?
I mean, but here you use Chinese.
You just use
the right
directly. Direct, exactly. In order to be for CP minus Q P P to be less than epsilon, let's say epsilon, let's say that less than less than epsilon, less than P to the how should I say this? Of order P to the minus M.
Means the min of the primes and see.
Yeah. Let's say P to the minus M. Okay, choose M so that P to the minus M is less than epsilon. Less than or equal to epsilon. Right? So I need CP.
You just wrote greater. Can you set much?
Yeah. Let's okay. What we want is this. Choose P to the M that's less than or equal to epsilon. P to the minus M. Choose M such that P to the minus M is less than epsilon. Then this thing is implied by CP. Well, what is CP? CP is in ZP. So this is some A0 plus A1P plus A2P squared and so on up to AM P to the M plus higher order stuff. Right? Then if that's CP, so CP minus Q is less than P to the M if and only if Q is congruent to this number mod P to the M. I guess I only need this.
This M is like dependent on the prime.
There's a different M for every prime depending on epsilon.
Right.
So the epsilon is fixed. Right, I'm given some epsilon. I only have finally many primes to consider. For each prime, I go and I say, how well do I need to approximate CP by? I need to get the first M minus 1 digits right.
Make it happy, we can take the biggest and
That's what I was thinking.
Yeah, you can make it uniform because these are finite sets.
Right.
So there's no issue like that. So in fact, what do we need? Okay, so let me finish writing. What we want is to approximate each CP with a Q within epsilon in the p-adic norm. So we choose an M so that P to the minus M is smaller than epsilon. If C has these digits, then CP minus Q is less than P to the minus M, if and only if Q is congruent to this number, A0 plus A1P plus and so on, plus I guess A M minus 1 P to the M minus 1 mod P to the M. Mod P to the M kills everything above. And if we want to do that simultaneously, we can by the Chinese remainder theorem. Okay, so the Chinese remainder theorem says not only does such a Q exists, such a Q exists in Z. You don't need the rationals. This has nothing to do with the rationals. You can find an integer that simultaneously approximates. So let's improve our weaker approximation. There exists an integer that simultaneously approximates however many p-adic integers you would like, a finite number of p-adic integers to arbitrary precision. And the argument is the Chinese remainder. Does that make sense?
I feel like negative powers might be just like translate.
That's exactly what we're going to do. Okay. Next thing is actually called, this is a real theorem called weak approximation. And it's the same theorem, weak approximation, given S and a set of CP in QP now, and epsilon positive, there exists Q in Q such that CP minus QP is less than epsilon for all P in S. Now you need denominators because that CP might have some, okay, let's write down the proof. Now your CP might look like some A minus N P to the minus N plus and so on. So if you take CP and you multiply it by P to the minus N, I don't know why that refuses to be a minus sign. Minus sign.
It really wants to be an integer.
Yeah. So then, again, you only have a fixed, this epsilon is fixed. So you apply the previous theorem, apply apply weaker approximation to CP p to the n, and then divide the q that you get in z, q in z, by the various p to the n's. Does that make sense?
What do you have to take this bit stronger than approximation?
Yeah, exactly. Thanks. With epsilon equals epsilon times p to the minus n.
Right.
Then divide the integer that comes out of that by the p to the n's, and you'll be within epsilon of each of these. Does that make sense? I'm not spelling it out in gory detail. Okay, let's spell it out in gory detail. Okay, so I take this. This product is now in ZP. So I take epsilon. There's a weaker approximation which takes a bunch of elements of ZP and some epsilon and returns an integer q. The epsilon that I send it is, so the epsilon.
You need to make it like even like some sort of like massive power.
Sure. Yeah. Yes. Yes. So I send this, and epsilon equals the min of epsilon p to the n's over the finitely many p to the n's that occur in this set S. Does that make sense? So that gives me a q, so that q minus cp p to the n in p is bounded by epsilon times p to the minus n. So when I divide by p to the n, now, so then the q, so this gives me a q, let's call it q star, right? So then the q that I want, this use, right, the lean tactic use, q equals q star divided by p, the product of the p's to the n's, divided by the product of the p's to the n's. Let me write this more formally. You want this cleaned up. So each P comes with a CP, and the CP comes with an NP. Maybe that's better. Okay, so each one, so apply weak approximation to CP times P to the NP. And with epsilon equal to the minimum of epsilon times P to the minus NP. Then I find a Q star, which is an integer, so that CP times P to the NP is bounded by epsilon P to, well, close enough, P. NP. Yeah. Okay, you see what I'm doing, right? Well, what does this mean? This means that if I take this Q star divided by P to the N, P, that'll be within epsilon of CP, because the norm goes the other way. When I divide by P to the N, that multiplies the norm by P to the N. Okay, now that's not going to, the other powers of P, the primes that are not that are not equal to P, change Q by a unit. Okay, so it doesn't change this thing. So you take a product of P NPs, and this satisfies what we want. Satisfies.
I probably have to check that it's still congruent to the positive power parts of CP, but it reduces them more.
Okay. Good. No, what you just said is making me nervous. Is this right? Yeah, because all we're doing is we're just shifting this so that it's in ZP. We get an integer, we divide. That shifts small. Okay, good. Yes. Okay. That's weak approximation. And now let's prove strong approximation. So knowing that we can approximate given some elements of QP, a finite number of elements of QP, we can find a single rational number that's within any epsilon of all of them simultaneously. So now let's prove the strong approximation theorem. theorem. Strong approximation. This is just what it's called. Well, there is something called super approximation, but that's yeah, that's another discussion. Okay, so strong approximation is that given X in the Adeles, it's the fundamental domain theorem. Given X in the Adeles, there exists a Q in Q such that X minus Q or plus Q, should we subtract or add? Doesn't make any difference. I'll add because whatever. So that X minus Q is in a certain set. We'll figure out what that set is. Certainly that set will be a product of ZPs. And then what goes in the real place, we were saying -1, 1, but I think we can do a little bit better. Right, adding is better. Can you guess what the set will be? 0 to 1, yeah, not -1 to 1, that's a little too big in the real place, but 0 to 1, because -1 is in all ZPs, and it sends something from -1 to 0 to 0 to 1. Okay, so we need this domain. I'll show you in a second. The set that we were considering before is -1 to 1 in the real place, and then a product of all the ZPs everywhere else. -1 to 1 is too big to be unique domain for every point, such that X plus Q is in, well, it's not in D, but it's in the closure of D. It's in the closure of D, meaning closed 0, 1. Everything else is already closed, compact. These are open compact sets.
How do we topology on this again?
It's the topology generated by, this is exactly the topology generated by this.
So like component minus closure over.
A finite, yes, yeah. So a finite number of these, and then a ZP, okay. Given an X in the Adeles, there exists a Q, a rational number, so that you can get in close brackets 0 to 1 cross ZP. That closure doesn't do anything. And so this is 1. Remember the fundamental domain. Where's our fundamental domain? It's a good thing that we wrote it down. You need to be able to bring everybody into the domain. The domain needs to be open, and it needs to be uniquely the case. And 2, if we have X and Y in this domain D, which is this thing, and X is equal to Y plus Q, Q and Q, then Q is 0 and X equals Y. Okay, let's prove the strong approximation theorem. All right, part 2 is very simple. Part 2 is, okay, X and Y are in D. What can I say about X minus Y? X minus Y, well, these are all a ring. And if I take something in 0 to 1, I subtract something in 0 to 1, I range in -1 to 1. This is in -1 to 1 cross the product of ZPs. And if this is a rational point, yeah, the only rational point, only Q point is Q equals 0.
-1 the whole time, that -1
Right.
Too big. Exactly. If we had put -1 to 1 here, then that difference could be from -2 to 2.
Right.
Which now does contain, or could, but it does contains 1 and -1. Okay. How about 1? Okay, so uniqueness is trivial or easy given what we already know. How about 1? How do we get inside this set? Well, first of all, how do we get inside ZP? Product of all the ZPs. Let's worry about that first. Okay, so we fix some X equal to X infinity, X2, X3, and so on in our set, in our ring of Adeles. Let S be the set of places so that XP is not in ZP. Those are the ones we're worried about, right? We're fixing X. S is a function of S of X, this set of places. Okay, and we know that this is finite by the construction of the Adeles. Doesn't look like an S. S is finite by the construction of the Adeles. Okay. So, well, it's not in ZP, that means it's in QP. These XP are in QP. So what are we going to do? Yeah, let's apply weak approximation. Okay, apply weak approximation with what? With S equals S, with S, these XPs, the XPs, and epsilon, how close do we need to get? Actually, we'll just need to get within 1. Because that is what will put us in, that'll means the difference is in ZP. S is finite by the definition of the Adeles, exactly. We fixed an X, a single X.
It feels like weak approximation is stronger than this.
It kind of, yes, kind of. It's a funny name. Okay, so we apply this. So there exists a Q. That means there exists a Q. We obtain a Q. Let me try to use terminology. We obtain a Q in Q such that XP plus Q in P is strictly less than 1. Less than or equal to, doesn't matter. i.e., this is in ZP, exactly as we wanted.
There's no interference with like other.
How do we make sure there's no interference with the other primes? Exactly. Make sure the Q, remember how Q is constructed. Q is really an integer divided by only those powers to only those primes that affect the calculation. So there's more information here. The more information is, and we can add it to the statement, and denominator of Q. We don't care about the numerator because the numerator might make our norm smaller, but not bigger. ZP is everything less than or equal to 1.
Yeah.
So we don't care about the numerator. And denominator dividing a product of P to the NP. Or just equal to, I mean.
So this Q star, what do we use?
So this Q star,
Q star is an integer.
the Q star was an integer, that's right, and the Q is a rational number. And I'm dividing by only those primes that appear here. So this is a unit. This Q, or an integer at least, this Q by construction is in ZP for, yeah, exactly. So not from the statement, but from the proof of weak approximation. For P not in S, it's in ZP for P not in S. This is by the construction, by the proof, by proof of weak approximation. And ZP is a ring. So when I shift those XPs, which are already in ZP by Q, I still have, I'm still in ZP. Okay, does that make sense? And ZP is a ring. So now what we have is that XP plus Q is in ZP for all P. In S, this is for all P and S. In S, it's because we applied weak approximation. For P not in S, it's because the thing that came out of the proof of weak approximation is in ZP.
So this study was saying, even if you had some numerator, it would still be in the ZPs because you just made.
Yep.
That doesn't.
Well, ZP is a ring.
Doesn't hurt like the uniqueness. Well, you're ready to be unique.
This isn't yet unique. What's going to make it unique? There's one place that's actually going to make this unique that we haven't dealt with: infinity. We have to fix the integer. The last step, once we found this Q, the last step last step, once we found, so this Q is fixed, this Q is in Q, we obtain this magical Q in Q. The last step is find an n, integer n, such that x infinity plus Q plus n is in 0, 1, or the closure of 0, 1. Which we can obviously do. That n is also in ZP for all p. So shifting by n doesn't change this fact.
I see. So it's like if you have, there's some other component that got preferred in my norm became smaller than 1, then 1. That's
Right.
sort of like adding some integer.
Yeah. Yeah, it's not going to change the fact that the norm is less than 1. We have this ultrametric inequality. We have this super triangle inequality that makes ZP into a ring.
I guess I'm still confused.
Yeah.
So like, I guess what I'm worried about is what says that in this process, I can get it to exactly the same place, but there's some ZP that, you know, in which the norm became like smaller.
It can become smaller.
But like in a unique way.
The uniqueness is part 2.
The part 2. It's like it is already in there, yeah.
Yeah. If you're going to shift by a rational number that makes one of these smaller, it's going to push you out of not this set, but this set. Because of the uniqueness, because there's only one rational number in this big product. Cool.
Seems like a similar amount of work to SL2.
It's not dissimilar to that. Yeah. Yeah, there's a lot in common. Those that are familiar with that argument will see a lot of similarity to this argument. Okay, so this is the number that we use. This is indeed a rational number, and it satisfies all the things that we do. Okay.
It's like the SL2 is the case of like doing the infinity prime only.
Yes, although it's a non-abelian group, there's sort of much more going on in SL2Z, but it's only happening at one place, whereas here you have to deal with all the places simultaneously, but actually only find many of them. Okay, I mean, let's see. Let's do an example. X is equal to pi, and then a third of type Q2, and then a third of type Q3, and then all ZPs after that. All elements of ZP after that. How do I move this into, what's the problem? Where am I not in my domain? Which Q, and it's unique Q in Q moves X into our domain D. Is a unit. Yep. So this is in ZP, Z2, no problem. I don't care about that one. There's only one thing that's bothering me. It's this 1/3. Well, there's two things that are bothering me. The first thing that's bothering me, let's follow the proof, right? The first, we want weak approximation. Should I make this less trivial? Should I put a 1/5 or a 1/2 for that matter?
Sure.
Okay, so let's put a 1/2. Okay. This is not in Z2 anymore. Great. So we have three places to worry about. How are we going to we get a single Q, we only get one chance, and we have to move this X into the fundamental domain, D. Yes, but in this case, it's very simple. Why don't I just take Q is equal to, isn't it 5/6?
Yeah.
Or -5/6? because a half minus 5/6. I mean, 5/6 is a half plus a third. This is a half plus a third. So if I subtract a half, this is minus a third, which is in Z2 when you cast it into Q2, whereas a third minus 5/6 is a half plus a third minus a half minus a third. So this is minus a half, which is in Z3. You see that? So if I take X and I add 5/6 to it, this becomes a unit. This becomes a unit. All the other, an integer. This becomes an integer. All the others were already integers, and this is an integer at all the other places.
Product of denominators and numbers. Some numerator is gonna have to work.
Right. Some numerator is going to have to work to kill off the parts that were problematic. And then what do I do about pi? So x infinity plus q is 3.14 minus 8.8.
0.86.
This is going to be 2 point something, 2.3, whatever. It's 2. Yeah, the floor of this thing is 2.
It's 2.
The floor of this thing is 2. Okay, so my final answer, q star, what did I call it anything? No, I just called it q plus n. So this is n. So q plus n is 2 minus 5/6. And 2 minus 5/6 is what, 11/6 or something. If I take,
Adding that thing?
yes, so
Adding that thing makes pi bigger, not smaller.
Right.
I think not minus 2 times 5.
minus 2 minus 5/6, that's even better. Yes. So yes, this number is 2, so I want n to equal minus 2. Okay, so then q plus n is very good. Don't make me do arithmetic. 17, negative 17/6. Okay, then x plus q is pi minus 17/6, and then a half minus 17/6, and then a third minus 17/6, and then this is already in ZP, so a bunch of ZPs. And this is in 0, 1, hopefully. And closure of 0, 1, and this is in Z2, and this is in Z2.
So these others, it's like if you didn't change it, just consider it like ZP.
It's a ring. It's a ring. So this is in ZP for everything except 2 and 3. And it's, look at that, there's a 17 in front. So it's going to have a norm less than, well, at least this thing. I don't know what's going on at x17.
Prime 17.
Yeah, the prime 17 is going to have norms strictly less than 1,
Right.
potentially,
Well,
depending on what's going on at x17. X17 was totally arbitrary.
well, but if it was an integer to begin with, at most it would have been 1.
At most it would have been 1, yes.
So it will have to get smaller.
It might stay 1.
Oh, like, yeah, like the power 17 might not.
Yeah.
Disappear.
Yeah.
Yeah.
Okay, does that make sense? So that's exactly what's going on. So any number you want, we'll find a rational number and a shift, so that when you add that rational number onto your x, the first component is going to be between 0 and 1. All the other components will be p-adic integers. Cool. That's the fundamental domain. Very simple.
Geometrically, how do you look?
I still think of it as just a circle with a bunch of compact stuff glued on top. I still think of it as, I mean, look at the domain, right? The domain is a circle. This is R mod Z. And then you just have like this compact stuff that you're gluing on top of it. But then you get to move that by Q and get all the Adeles. Yeah.
It's a strange picture.
It's a slightly strange picture. Takes some getting used to. All right.
Difficulty visualizing ultra vector spaces in general.
That's right. That's right. I don't know. I do think of QP. I mean, QP itself, just a single QP. I don't have like Q3 I don't have trouble visualizing that much that, you know, you get 3 choices for A0, and then you get 3 choices for A1 and A2. But this, of course, came from 3 choices of A-1. But you're only allowed to go finitely many steps in the bad direction, but infinitely many steps.
Doesn't look isosceles.
Yeah. But visualizing this is just a tree. It's just a tree with, you know, a finite set of steps that way. Yeah, it's a fractal. Yeah. That is how I think of Q-street. Anyway, all right. I want to get to Fourier analysis, but I also want to tell you about the ideles. We've sort of been hinting at them time and again. Let's just get to the ideles so that we have them there. And historically, they appear before Adeles. The ideles, A star, is the set of X equal to X infinity, X2, and so on. Because it came from ideal numbers, ideal elements, and ideals. Because French.
Okay.
Chevalier. Yeah, I gave this thing. Yeah, it comes from French. So each of the XPs are in QP cross, which just means they're not 0. And almost all XPs are in the unit group. Now I really do want the norm to be 1. One specifically. Units, yes, exactly. For all but finitely many places. That's what this AA, almost every place. Okay, so at every place, for all P, we have an element of QP cross, not 0. QP is a field, so the only thing that's not invertible is 0. And only finitely many things are not in ZP. Okay.
So that includes ones that might be like in ZP but not a unit. Those are still allowed finitely.
Finitely many of those are allowed.
Okay.
That's right. In fact, that's exactly what the finitely many exceptions, the finite list is.
Well,
Oh,
you're also allowed to have stuff that's not in ZP at all.
That's right. It can have things to the right of 1, to the left of 1, start to the left of 1 for finitely many things, and then everybody else starts at the constant and non-zero constant term. Does that make sense? Okay. That's the ideles. What else do I want to tell you about? Oh, yeah, like this. Sorry, say it again.
Why didn't the second condition
Because in the Adeles, okay, in the Adeles, if we look at this as an element of the Adeles, which it is, it's an element of the Adeles only require that almost every P, for almost all P, all but finitely many places, XP is in ZP.
So we could just say that it's a unit.
In every component, it's a unit after a certain number of places. Well, that's exactly what, yeah. Yeah, exactly right. So this becomes invertible elements in the Adeles. So this is a group. So the ideles are a group. The Adeles are a ring. The ideles are a group. So this is a group. Yes, all primes, including infinity. That's us less than or equal to. Okay, so for infinity, it means the reals, the non-zero reals. Okay, so this is a group of ideles because if I take an x times a y, right, I'm multiplying pointwise, x2 times y2, x3 times y3, and so on. And eventually they will all be units, and the units form a group.
I don't know if this is ever going to matter. When we say, like, for all P less than or equal to infinity, something involving Z, does the infinity mean like the normal infinity we know? Does it mean like the interval -1 to 1?
Yes, very good question. So here I want for all P less than or equal to infinity, and here I don't care. Here for almost every P always excludes the infinite prime.
doesn't matter. So is the answer like we will never write Z infinity to mean anything?
We will not write Z infinity to mean. Yeah. Maybe there are people who do. I won't. Unless I do. But I don't think I will. Right. So this is a group. All of these things are invertible, and they're invertible because what's 1 over 1, 1 over x. 1 over x is 1 over x infinity, x infinity. I mean, it's just the obvious thing, right? 1 over x2, and so on. And only finitely many of these will not be like all the eventually, these are all in ZP cross. So they're invertible. And everything here was non-zero, so it's invertible. So you can divide. You cannot add. The sum of two ideles is not an idel, but a product of ideles is an idel. Okay, so it's a group. It's a multiplicative group. Multiplicative group of ideles.
Right, you can have an element and it's additive inverse to both the invertible. So you can add them and then just get 0.
Sure. Yep. Yep. 1 plus or negative 1. Anyway. Yes. Yes. What's the topology? Let's get a topology on ideles. Topology. Okay, so what's this is actually a very good question. What's the topology? What's the basis? That's so what do you mean?
Yeah, so before we move to the side play and generated by an open interval in R, and then the Z peaks. So I want to say like an open interval in R without 0. And then I'll Z peak process.
So I've heard two things. I heard UP is open in QP cross for P and S. So we take a finite set of opens in QP cross and then take a product over ZPs for the rest of the places. I also heard restricted topology, or
It is actually a subset of the other thing.
this is for sure an open, yeah, this is a nice open set, or
And
is it?
like the space is like literally a subset of the other.
Yeah.
Yes, exactly. The space of ideles is literally, any idel is contained in the adeles.
So you can literally restrict topology.
You could. You could, or the subspace topology.
And it's better. Yeah, yeah, like all I was doing was taking the same basis and removing the literal points that don't exist.
These topologies are not
No.
same. The same.
No.
And in fact, the subspace topology was the first proposed. And it turns out it's not the right one. And I think I think Chevrolet got this wrong. And they fixed it up. This should be the basis. What's the difference is subtle.
Somehow, like doing the basis directly is going to be easier, but then like drawing an extension into the ideals would be a little bit harder.
Well, let's see. How are they different? Okay, so now I'm going to take, let's call this VP cross product of over primes of ZP. This is P in S, this is P not in S. So that's a nice open set in the adeles, and I'll intersect that with the ideles. Why is this not the same?
Is VP like completely arbitrary?
Yes, VP is open in QP. Open in QP. Okay, let's call these sets X, and let's call these sets Y. Why are they not the same? This was very subtle and caused professional mathematicians who were inventing these things much angst when they realized that something was wrong.
There's like feuds, like some mathematicians fighting over which one.
I mean, the literature contained this one before it contained that one. So there was a bit of a feud in that this one was realized to be the one that is necessary to do analysis. It's so subtle. It's very hard to see the difference.
Sweet, in those bunch of years that you wrote about, like by when Was it already like?
I think this is still 1930s, mid-30s, mid to late.
Oh,
30s.
okay, so this is like a long time.
Oh, not that long. I mean, these things were not mainstream until after, I think significantly after K.
What I mean is it didn't take like late forties or fifties, they already like. Knew that you should pay.
Yes, by then they knew that this was the right basis.
Six pieces.
Yes.
Okay.
Like, so each, so like, you're doing an infinite intersection of. Oh, wait, no, that's just one set.
What's that? In this one. Why? But I have to intersect with a star, so. Here's the subtle difference. Should I tell you, or you want to think about it for a second? It's very hard to see. Nick is gonna tell us.
Well,
ZP remove 0 is not ZP times. That's true. That's true. But here, when I intersect, that's true. That's not the,
yeah, I don't think we have.
because when I intersect this with the ideles, I do want all but finitely many, like the only elements little y. So let's take a little y in y. What's a typical little y in y? A typical little y looks like some y infinity, y2, and so on, yp, and all but finitely many of them will be in ZP cross. So that's true. ZP take away 0 is not the same thing as ZP cross.
First chunk are banned from being 0.
That's right.
But
These are all
it could
non-zero.
be any-
They could be anything else.
Okay, so that's what an arbitrary element of that set is.
Yes,
Now let's figure out what an arbitrary element of the other thing is.
it looks exactly the same
Okay, just checking.
because they're both, that's what any element of A cross is.
Get it done.
It's not the elements, it's the sets
Right.
that are different. What's special about this set? Nick's got another suggestion. Sure, for each y and y, yes.
If you just say those sets have exactly the same elements, but the sets are different.
No, the how each element in each of those sets looks individually is the same, but the sets themselves are not. But it's not the same P where you're eventually in. That's exactly, yeah, okay. Well, Nick, you know this stuff. You're not allowed to say. Yeah, that's exactly right. It's the uniformity. It's the uniformity, the difference is the uniformity in S. Okay, given X, there exists an S such that for all X in X and for all P not in S, X, yes,
Together, okay.
yes, together eventually constant as opposed to in singular individually eventually constant. This is in ZP cross. It's very subtle.
So this that y is actually usually
Yes.
the open space.
That's right, but we don't want to take the, yeah, so we want to more restrictive basis.
That means the topology in the first one is binary.
Yes. It's a stronger, yes, exactly. Given y, for all y in y, there exists an S which depends on y, such that for all P not in the S of that y, YP is in ZP cross. Yes, it's a matter of, if I want to do an integration on one of these open sets over the ideles. If I take X as my basis, I have one fixed set of places. X is up here, product of UPs and then product of ZP crosses.
And this one was the.
This is the correct.
Restricting the basis.
That's right. This is picking the natural basis for this topology, as opposed to the subspace topology. Why is the subspace topology?
Okay, and then.
Okay, if I want to integrate over X, I know that every single element of X after the 27th prime is in ZP cross. Any set X comes with a set S, so that everybody is in ZP cross after
After a certain
that
point.
fixed set of bad primes. Whereas in Y, if I just do the obvious thing, which is to take the subspace topology, these guys all have very different places where each one of them individually has a place where they are eventually in ZP cross.
Yeah.
But the totality, there's no uniformity in the set S.
I'm not seeing that class.
Well, it's just that,
Can we look down a specific example of a set that's in one of the bases but not the other?
well, this is it. This set,
I meant
This-
this little, look at there.
right? This set
There's no way to
already,
make it clearer with it.
it doesn't make it any clearer with an example.
Okay,
Yeah.
fine.
I mean, this set already contains, it's all the elements here, which have arbitrary many, like when I intersect this with a star, with the ideles, all I'm saying is that I only want to take out those elements from this sequence that are eventually in ZP cross. But I'm not saying how far you have to go for that eventuality. And there's going to be a different eventuality for every element of, there are going to be infinitely many choices of this eventuality.
For every time.
The eventuality means how many primes I have to go.
Right now, like the infinite sequence where like all the elements can be in the same set in the subspace topology.
Yes,
They can't all be in the same set.
Yes. very good, very good.
That's what I meant by specific.
Okay, so example, sequence that is in Y, but not X. That's what we want. Okay, so here's a sequence. I want Y equals whatever. If I take, I mean, just let's just put a 0 in the real place. That makes no difference. Oh, I can't put 0 because that's not going to intersect a star. Let's put a 1 there, and then let's put a half, a third. Yeah, that's right. A half, a third, a fifth, a seventh, but then ones all after that. Okay, so this is Y sub 7 or 3 or whatever. However you want to index
The
these.
next element of the sequence, that the one after 1/7 would be a 1/11.
Exactly. Exactly. Okay, so this sequence of YPs is a subsequence of Y. That sequence of YPs is not a subsequence of X. This has arbitrarily many bad places before you get going, whereas X comes with a fixed set S of places beyond which everybody's all ones. Does that make sense? Joy, does that answer your question? This is very subtle. That's why it took people a while to figure this out and get it right. So what we want is this basis. We want this basis and not the subspace topology. No, just can we find a sequence of points so that all of those points are in Y, but there is no choice of X for which that sequence would be a subsequence in an X, in such an X. Never mind Cauchy or converging or anything. Just give me a sequence.
I thought they're the same as set was.
So if you give me the set -1, 1 and all ZPs, and you intersect that with a
So there.
hang on, let's do it like this. Let's do it like this, and you intersect it with 2, 3, 5, 7. That's better.
You're saying that's like the 7
That's the seventh, yeah, or whatever, if I index, yeah, Y7, yeah, oh, yeah. So these numbers are all in ZP,
Yeah.
okay? And so these elements will all be in this set. They are all ideles because they're all eventually one, but they're not uniformly eventually one.
You
Okay,
can't write down any sentence that will contain all of them.
There's no set X. There does not exist an X in our topology
When
containing.
when you're writing a set X, you say, okay, and then after this place where ZP cross. But go far enough in that sequence and like that'll violate it after that place.
Yeah, so it's about the uniformity in the set of bad places. There is no uniformity in the set of these bad places. This will get arbitrarily far into the bad places. This sequence has arbitrarily many bad places. It is a sequence in the set Y. It is not a sequence in any set X.
Why are we using these sequences?
Well, that's one way to see the difference between the
We're showing that,
topologies.
like they're not the same basis. Here's a sequence that they can all be in the same open set in subspace topology, but they can't be in the, at least they can't be in the same basis.
There is no basis containing this sequence. Anyway, all right. So like you said, it takes some thought to figure this out. Let me get, okay, so we're obviously not going to get to full Fourier analysis and Poisson summation, but at least let's get to character. So back to Adeles. We don't need the ideles for a minute, but I wanted to at least touch on that. Back to Adeles. What did we do when we got QP? We wanted to do Fourier analysis on it. So in order to do Fourier analysis, we needed a character. So what's a character? Character on the Adeles. How can we construct such a thing? On each QP, including infinity, we had the character x maps to e to the 2 pi ix. Right? So this is a homomorphism. Yeah, it's an additive homomorph. It's a group homomorphism where the group law here is addition. The group law on the multiplicative complex numbers is multiplication. I want the yes, and on R, this multiplication, and on the QPs, by the way, maybe this is a place where I'll write Z infinity. On R, this is invariant under Z, under the action of Z. In other words, the character is trivial on Z, i.e. character is trivial on Z. The same, yes, same for ZP, right? What we wrote down, the character that we wrote down for each QP was trivial on ZP, right? It took an element XP equal to A minus N P inverse up to A minus 1 P plus A0 plus A1 P and so on. And exactly, none of this stuff matters. It takes it to E to the 2 pi I, bless you, A minus N P to the minus N up to A minus 1 P inverse. Everything else is an integer or the limit of integers. And so the character just chops it off. How do we make a character on A? We want a character on A that's trivial on the discrete subgroup of A, which is Q.
R version before you put Y to the S and whatever.
Y to the S is the multiplicative character. This is the E to the 2 pi I character. We will also need characters. We had norm P to the S, which is a character on the multiplicative p-adics, which we'll do for the ideles, but that's coming later.
Oh, okay.
We're just working with the additive group. Well, there's one natural thing that you might think to do. Let's try take x infinity, x2, x3, and so on, and map it to the product. Yeah, the product over all places, including infinity, of, let's call this EP. Should I call it EP of XP? Where each EP of XP is e to the 2 pi I XP in the appropriate meaning of that expression. That almost works. That almost works. It turns out that what you want is E infinity of XP to be e to the minus 2 pi I x infinity. For the same reason, you'll see in a second why we want this. I claim that this is trivial on Q. So is it clear that this is a homomorphism? Eventually, if an element of A is something that eventually is in ZP. The character is trivial on ZP. This product is always finite, right? Product has ones after, except for almost everywhere. Yes, everywhere, right? But in A, there's different for any X, there's a different point after which the product is finite, but the distance you have to go for it to become finite varies. Why? So my claim, maybe I can prove this now. My claim is that for all Q in Q, except 0, actually 0 is just fine, nothing wrong with 0. For this is an additive group, it had better not see any difference between 0 and any other rational. Let's call this Adelic. This is EA of X. EA Q is 1. I claim that this thing will be trivial on the rationals, on this discrete subgroup. Do you kind of see why? At least in your heart? Yes. Yes. This is the coercion of the rational into the diagonal embedding of that rational number into the Adeles. That's right. For very few P's. Yeah. For almost all places, it'll just be 1.
Q is some power of P.
That actually is a good point. It's a character, but we have to be a little bit careful, I guess, with things like taking roots. So for example, n, if I have a natural number n, I know that, yeah, okay, let me not try to rush this argument. This is where we're going to start next time.
Take X infinity and subtract off like all of the individual ones to get an energy. Kind of. X infinity is going to be Q itself. So at some point I have e to the minus 2 pi I Q, that rational number Q. So whatever is happening at the other places has to exactly counterbalance that. Yeah. And indeed it does, but you have to be a little bit careful about how, because the rationals, wherever you have denominators, you're actually going to get some expansion, some initial term of that expansion. And it's a little subtle how that turns into this product formula. So let's do this next time, and then we'll get to Poisson summation.